No one's ready really to go at 8 o'clock. Even the computers are rebelling. Okay, so again, we are going to be covering epidemiologic data sources and measurements. I kind of went over the objectives already, so you can read those. Okay, we're also going to talk a little bit about some of the special issues regarding rates. We'll see there's a difference between rates and risk when you're observing a population, so we'll kind of compare some of the differences there. And then we'll also look at some of these commonly used rates to reflect maternal and infant health as a kind of a real-world example. So some of the data that we're gathering for some of these health analyses, the first thing you want to look at is going to be what your denominator is. So in this case, the denominator is going to be your population at risk. Very frequently, the best source of kind of widespread population data that we have can be things like the census statistics that are oftentimes used in the denominator. So if you're looking at, number of car accidents that occur in the U.S., that denominator is typically, your whole U.S. population. However, if I was looking at something like maternal health and infant mortality rates, what do you think my denominator would be in that case? Like pregnant females, perhaps, right? Because the whole U.S. population would include a whole lot of men, a whole lot of people that maybe could not get pregnant. So again, that would be skewing your data. So consider who your population is that you're looking at specifically, and if that makes sense. And then the numerator data is going to be defining the events or the condition of concern, so whether it be death or whether it be cardiovascular disease, whatever it happens to be. And so we can get this information either from health registries, disease, birth, death registries, all these different things, and surveys can be used in order to help generate that numerator data. So many nations will conduct censuses periodically. So here in the U.S., we do ours every 10 years. We do it on the year that ends with 0. So in 2020, we'll have the next census likely. And basically, it's just an idea to get kind of what the characteristics of the populations are in the U.S. And so we'll see that there's some inherent problems with looking at census data in just a little bit. But using the recent census data and for denominators, and then also looking at birth and death rates, you can end up generating these vital statistic registration systems, which can generate a lot of this data for us, specifically for like our denominators. So access to the recent statistics of various countries is needed oftentimes to make international comparisons, especially when you're looking at mortality rates. And this will be important when we're comparing, especially when we're looking at how to compare apples to apples between different countries, because we'll see that based on those population differences, you can see they can kind of skew your numbers unless you're looking at it consistently. This is actually a good website if you ever want to go out and look at kind of all of the collation of all this different information here. We can see populations of different countries and death rates and et cetera. Of course, not all countries are going to have effective disease reporting systems, so obviously your more well-developed countries are going to have a little bit more robust systems than those maybe a little bit more on the developing side. So most birth and death data and then many other types of health-related statistics are going to be coming from these public data systems. And again, the collection of data is frequently going to involve both the local, state, and then the national agencies. Again, you'll find that data on birth, deaths, the causes of death, fetal deaths, marriages, divorces, all that's going to be collecting kind of locally by Registrar of Vital Statistics, and then that'll end up getting kind of force-fed up through the system, and it'll be collected federally as well. So I remember when my baby was born, had to go through and actually do the birth certificate and all that fun stuff, and actually get her social security number, and now she's kind of being tracked by the government forever, right? Yeah, essentially. Again, so basically, state governments can use this information as well, again, about their local areas, and then that can, again, gets fed up through the government, where we can see that the National Center for Health Statistics is one of the big branches of that, as a branch of the CDC, which is useful for preparing these kind of national summaries. Again, the U.S. Census is undertaken by the federal government specifically, and again, it's going to be around April 1st, done every year ending in 0. So as I mentioned, 2020 will end up being the next one. And then you can use that information for population projections to estimate the size of the population between censuses, beyond just the most recent data. And so what do you think are some of the inherent problems with using census data? Yeah, did you get everyone? Like, who might you miss? Homeless people, good. So if they don't have a home for the census people to go to, maybe they don't get captured. There could be other ways you can capture those people potentially if they're signed up through some, if they had some sort of like halfway home or something like that. Who else might you miss? Yeah, so undocumented immigrants might be another big one. So we'll see how that changes in the next 4 years, right? Anywho. So we know that there's going to be some inherent issues with the census data and that being so accurate. Yes.
How do they do like jails and hospitals and stuff? Do they take that into consideration?
They would probably take the jail data into consideration, but especially if you have like long-term care centers and things like that, I imagine they would count those patients. But like acute care stays and things like that, I don't know that you necessarily need to worry about that because oftentimes they're talking to someone else in the home who would count you, whoever the patient is in that scenario. Yeah. So again, usually you're going to see with clinical epidemiology, which again is kind of applying these epidemiologic principles to your individual patients. You're going to find that a lot of health-related data is going to come from examination of the patient, clinical records, and also studies of specific clinical populations. So in the instance we were talking about, maternal health and fetal health, things like that, that kind of goes back to that situation. So, and then when monitoring the health of large populations, as much as use as possible is made of existing databases. This helps to kind of reduce costs and help speed up the answers that we can get. So if you have a large repository of data that you can go to and pull information quickly, that's going to be a whole lot easier than having to go back and do the grunt work yourself, right? So you'll see a lot of epidemiologic pieces will pull data from these registries in order to help kind of generate the data a little bit quicker. So the federal government is going to collate data on all these different events, as I mentioned. Local and state officials initially are taking the data, and again, it'll get fed up through. Now, the analyses are only going to be as good as the data on which they are based. So as we mentioned, a few inherent insufficiencies in the current way we're monitoring these things to begin with. But they work to make the data as accurate as possible. So you have to take it with a grain of salt that you're going to be missing some people in this information. So again, if you have unreported births or deaths, if you were to have inaccurate death certificate diagnoses, so how often do you think that happens? Probably pretty frequently, right? Like, so if someone dies of pneumonia, say due to influenza, what do you think gets written down on the death certificate? Probably pneumonia, right? And even they might not even mention the influenza, which can be an important component of that. We'll talk more about that in the next lecture. But just keep in mind that things can be inherently inaccurate if the data is not being collected appropriately, especially if it's by the on-call physician who's working at 3 a.m. and is super tired, and they just like, what it was pneumonia, kill them, right? Things like that can be inherently full of error. And then, just looking at the erroneous demographic and clinical data on both birth and death certificates. So we also know that we have good reporting systems for certain communicable diseases. So certainly physicians, hospitals, clinics, laboratories in the U.S. are required to report all cases of many infectious diseases up through the CDC. So we kind of talked about that previously. We mentioned that meningococcemia case I mentioned that would get reported up to the CDC. And we'll see that there's also some problems with that as well, because again, we'll talk about different types of surveillance, but this is essentially going to be a form of kind of passive surveillance in which people are voluntarily offering up information, right? So if they're not offering up the information, the people who are running the registries are never going to know about it in the first place. There may be some variation in reportable diseases from state to state, but here's kind of a big list of things that are commonly reported up through the CDC. So you can see quite a varied list here. Notice some things that even one reported case of could be a really big deal, right? We'll talk about epidemics and outbreaks and things like that soon. But essentially, even one case can sometimes be evidence of an epidemic that's occurring with some of these more rare conditions. So again, only a fraction of the actual disease cases are really reported. So what do you think are some reasons why we might not report some of these diseases?
Don't have time.
Good, so if you're too busy, you don't have time, you're not going to do it, right?
Somebody doesn't know it's supposed to be reported.
Okay, yeah, so if the information's not out there, they don't know that it's supposed to be reported. It's a good one. What else?
I think they don't check for it. If somebody dies before you have time to check for it.
Yeah, sure. So if you don't actually have the diagnosis, or if you have an inaccurate diagnosis, that could be another one that could skew the information there. Anything else? It could be just things, people are maybe shy to report these things. They worry about maybe having follow-up investigations if there's issues there, especially if it's something that was, could bring social isolation. So things like immunodeficiency virus, can be very devastating to a person. So they may want to keep that sort of thing private. Sexually transmitted diseases, TB, all those sort of things. So oftentimes you're going to find that a lot of these reportings are going to be underdiagnosing or underreporting for the most part. So say, for instance, when we talk about the National Poisoning Data System, so all the poison centers, all their cases get, whatever they get referred, both from the hospitals and from the lay people, gets reported up to that national database, right? So do you think that's underreported or overreported cases?
How would you overreport?
I guess not. I guess. So do you think the data is super accurate, or do you think it's underreported? Maybe they call twice for the same case. Sometimes happens. Probably underreported, right? So for one, if a patient comes into the ED and they say say they got caught by the cops and they were smoking marijuana out in the streets, right? And they had some other reason to come into the ER. Do you think the physician is going to call up the poison center to report this case of marijuana exposure? Marijuana poisoning, right? They probably have better things to do, right? So again, now if you had someone who was overdosed on amlodipine and their blood pressure was 50/20 and they were on death's doorstep, do you think that will get reported? Yeah, same thing goes for other types of diseases as well. So really the more serious cases tend to be more reportable because again, they're more dramatic. You may need some extra help with things like that. More minor things might get underreported. Very frequently we have cases where providers are very comfortable, especially ER providers are comfortable handling poisoning cases, and they may never call us in the first place. So again, if the registries don't get reported to, we never know about it, and we can't have the full data picture. So that's what you'll see, especially with poisoning literature, that very frequently, if they're pulling from the MPDS, that things are going to be underreported. Specifically, when I was talking about my coral snake literature, again, if no one called us about a coral snake case, I couldn't include it in the study, right? So just keep that in mind, that typically underdiagnosing or underreporting is going to be pretty common here. So again, especially for less serious conditions that are very frequent, you may not have as much reporting of that as well. So such statistics could still have definite value, particularly if the diseases are preventable by a vaccine. So why do you think that is?
So we know where to put public health resources.
Potentially. So it could be indicative of some other problem that's going on. So maybe there's a bad batch of the vaccine that's out there that's not providing actual immunity in that case. Or maybe there's some sort of change in the disease state to where the vaccine is not working quite so well anymore, right? So especially when you think about influenza and how sometimes we mispredict the strains that are going to be most prevalent that year, you may end up having increased incidence of influenza even though people were getting vaccinated. Things like that need to be reported because it's important in order to track that data. So, as long as the proportion of cases that are being reported remain somewhat constant, the pattern revealed is usually going to be pretty useful. So we know there's going to be some under-reporting going on, but as long as you can keep the reporting that is happening pretty constant, you can look for trends, you can look for changes that are occurring over time. And most often they're going to reflect the actual trends that are occurring with the distribution of the disease in question. So we can also look at different behavioral risk factor surveillance systems. So there's lots of different ongoing surveys and behavioral risk factors in the U.S. population carried out by different departments, health departments, and along with the CDC. Remember I talked about that article that I maybe coerced my future wife to move in with me? That was from the CDC, right? They were doing behavioral kind of statistics, saying like, okay, what were divorce rates like based on cohabitation beforehand? Not anything to do with communicable diseases, but basically, divorce is pretty bad, so we don't want to do that. So again, looking at all kinds of different type of behavioral data as well. So some of this can be done through random sampling. Sometimes they'll do kind of phone interviews. They may look at random sampling at different locations. They may just kind of take all comers that approach them. And so you can look at all kinds of things like alcohol consumption, smoking, obesity, all kinds of things. And so there's actually some very interesting ones, just to go back to the poisoning side of things, to look at illicit drug use in children. And so one of the studies I use frequently when I'm doing like school health talks and things like that, there's a study called Monitoring the Future, where they actually interview anonymously different school-age children. So they'll do like 6th through 8th grade, 9th through 10th, and then 11th through 12th grade students to find out, how easy do you think it is to get these different types of drugs? Like how often do you use these different types of drugs? The idea being that you want to use the data anonymously so that way they're more likely to be truthful when reporting that. But again, you always have to take it with a grain of salt, saying like, well, they might still could be lying, they could be exaggerating their answers, who knows? But hopefully by looking at trends over time and assuming that the data is staying somewhat constant, you should be able to get some idea of the true trends that are occurring. Just another good example of behavioral risk factor surveillance that occurs. You can also get a lot of data potentially from third-party payers. So over the years, different medical insurances have been collecting more and more data about their patients. Especially because if they're paying for this stuff, they probably want to see, who their patients are and are their interventions being effective. So you can have data coming from things like Medicaid, Medicare, the VA. Also, have you guys ever heard of Kaiser Permanente? That's a big one out in like California. They do a ton of information, a ton of studies through their patients that they collect all from the hospital stays and things like that. So oftentimes they're used by clinical epidemiologists and healthcare researchers who are concerned with patterns, and also if they're looking at the cost effectiveness of medical care. Because of course with a lot of those companies, the bottom line is usually a pretty important consideration. So they want to see if they're going to implement some change. It could be a formulary item on their drug list, or it could be a certain type of procedure they're going to cover. They want to make sure it's going to be cost effective for their patients, increase quality of life, increase quantity of life, while not costing way too much money. Okay, so now that we know where some of the sources of data are going to be coming from, we can look at some of the measurements that we're going to use when looking at this data. So first thing we're going to look at is going to be frequency. So as you might imagine, this is the frequency of a disease, injury, or death. It can be measured in lots of different ways. It can be related to different denominators. So again, different populations that you're going to be looking at. And then depending on the purpose of the research and the availability of the data, how you're going to be able to look at that, the frequency of a certain event occurring. So we've already kind of mentioned the difference between incidence and prevalence before, but we'll kind of go into this in more detail as it relates back to epidemiology. So the incidence is going to be the frequency or number of occurrences of a disease, injury, or death in the study population during the time period of the study, right? So is this going to be more of a prospective thing that you're measuring, or is it going to be more of a retrospective? Should be prospective, right? So you're starting with a population who maybe doesn't have any incidence of the event you're looking for, and you're looking for new occurrences over time. So again, the number of transition from well to ill, uninjured to injured, alive to dead, whatever it happens to be, you're looking for new cases of it, or new incidences of the event occurring. Sometimes you'll see it used incorrectly to mean incidence rate. So to avoid the confusion, we'll talk about rates a little bit later, but it may be better to use the term incident cases rather than incidents. So by saying incident cases, these are new incidences of the event occurring as time moves forward. Then we talked about prevalence. Oftentimes this can be also referred to as point prevalence. We'll talk about some different examples of that in a little bit. But basically it's the number of persons in a defined population who have a specified disease or condition at a point in time. Usually whenever your survey is done, or could be any point in between, right? So if you are looking at a specific population kind of more retrospectively, or you take a specific slice of time, how many people have that condition? That would be the prevalence of it, or the point prevalence at that point. Again, sometimes it gets used incorrectly, very similar to incidence. So we'll talk about prevalence rate a little bit later, but to avoid confusion, you can use prevalent cases to really mean as kind of a preferable term. So the difference between point prevalence and period prevalence, we'll say here that the term prevalence is used point prevalence is meant really. So at one specific point in time, we're saying this is the prevalence of the condition. Period prevalence is going to be a little bit more broad. It's referring to the number of persons who had the disease at any time during the specified time interval. Okay, so I'll show you a graph in just a minute to kind of show you some of the differences between these. But period prevalence is really the sum of the point prevalence at the beginning of the interval plus the incidence during whatever interval you're looking at. So again, you kind of take it at the very beginning and kind of at the end to see where you're at. So because the period prevalence is a mixed measure composed of point prevalence and incidence, typically it's not really ideally used for scientific work. So you won't see this used too often, but I'll give you an example of what it looks like just so you can kind of make heads and tails of it. So illustrating these morbidity concepts, so the concepts of incidence, or in this case, incident cases that are occurring. Point prevalence, period prevalence are illustrated in the next slide, so I'll show you what that looks like in just a second. And so the figure is going to be providing data concerning 8 persons who had a given disease in a defined population in which there is no immigration or immigration. So what does that mean? That last point. Yeah, so no one moved in, no one moved out. These are the same 8 people throughout the whole time, right? That's important because that can change your denominator over time. It can change your numerator as well if you have people who have the disease that fall out of the study period because they say move out of whatever reportable. Say you're looking at a certain area of the country and they move out of that, then you're not really able to track them any further. So a line will begin when the person becomes ill, and it ends when that person either recovers or they die. And so then the symbol here, T1 is going to signify the beginning, and T2 will be signifying the end of the study period, or Terminator 2, whichever one you prefer. Just kidding. T2 is the end of the study period. Okay, so you can take away a few different points here based on what you're looking at. So what can you kind of surmise about person 1? Yeah, they were basically ill. They had the condition the entire time of the study period. Okay, what about number 2? Yeah, so they started with it, right? So they're not like a new incident case in this period. They began the study with that condition, and they either got better or they died. And then someone like number 4, what do you think about them? Don't have to be so morbid about it, man. No, they got it, and then so they either recovered. They could have recovered. We don't know, or they could have died. So glass half full, half empty kind of situation. But anyway, so there were a new incident case during that time frame, and then either something happened where they did not have the condition any longer. All right, so I'll show you the next slide in just a second where we kind of summarize some of these their data points. So try to add the small picture here so you can at least keep it in mind. But so in case 1, the patient was ill when the year began. It was still alive, still alive and ill when it ended. So we kind of correctly surmised that. In cases 2, 6, and 8, the patients were ill when the year began, but then recovered or died during that year. So you can notice why they have the point on the right side there. And then 3 and 5, they became ill during the year and were still alive and ill at the year ended. So you notice how they have the point on the left side, but they continue past T2 there. And then in cases 4 and 7, the patients became ill during the year and either recovered or died during the year. So you guys are kind of spot on about those points there. So on the basis of the illustration, you can kind of make the following calculation. So if we were looking at the incident cases, so again, these are going to be cases of new incidence of the condition. So you would start at T1 and you see any new conditions that started as you move forward during that time period, right? So in this case, it would end up being 3, 4, 5, and 7. That make sense? The new incident cases. The point prevalence, say at T1, so those would be all the people at the very beginning of the study period who had the condition you were looking for. So again, in that case, the prevalent cases would have been 1, 2, 6, and 8. All right, so you're just taking a single point in time. We're taking T1 and we're saying who has the condition at that point. So there you can say there's four point prevalent cases. And then looking at T2, looking at the end of the study period, you can say the point prevalence was 3, but they had cases 1, 3, and 5, because those people still had the condition, had not either recovered or succumbed to that. And then if you were to look at, say, the period prevalence, so again, this is where we can say, what is the point prevalence at the beginning of the time frame to whatever interval that we're setting up. Here, we can say the period prevalence is equal to the point prevalence of T1 plus the incidence between T1 and T2. So in this case, we're going to say who all has a condition at the very beginning of the study period and who also developed it during the study period. So in this case, it'd be 4 plus 4, or it'd be 8. Right? So everyone had the condition at some point during this time period. Does that make sense? Again,
The last one?
Yep. So basically, the period prevalence, all you're doing is saying, I'm going to take 1 point prevalence, and then for whatever interval I'm looking at, I'm taking all the new incident cases during that time frame. So in this case, if your period prevalence, you're looking between T1, which is you're going to use as your point prevalence, which is 4, right?
Are we looking at that are we talking about that same picture again?
We're talking about the same picture again.
Can we look at that? And
I don't want to mess up the recording, but if you guys want to scroll back, no worries.
so it's the T. I can come to you after.
Okay. Oh no, I want to make sure everyone has it. But anyway, so I'll kind of go back to that. But so even though a person can be an incident case only once, they can be considered a prevalent case at many points in time. So I'll show you what that looks like in just a minute. Okay, so again, so if we're going to do the period prevalence, we're going to have to specify our 2 time points. So in this case, we're going to be using T1 and T2. Get my handy laser pointer. All right, so again, this is going to be our first initial time point, and this will be the end time point for us, right, just for ease of use. For our period prevalence, we're going to say initially what's our initial point prevalence. Here we can say it's going to be case 1, 2, 6, and then 8. That make sense? Okay, so then after that, for the period prevalence, you're going to take new incident cases that occurred during this interval. And so I can say, okay, I'm starting with 4, and then I found 7 was a new incident case, 4 was a new incident case, 3 was a new incident case, and so was 5. So basically, I'm looking at 4 plus 4, or your period, your point prevalence plus your new incident cases to make your period prevalence. And that's 8, right? Good. So again, even though people can only be considered a new incident case only once throughout the time frame, so really you can only consider 4 as having 1 new incidence here. Looking at the point prevalence, you can measure that anywhere you want. So again, the point prevalence can change if I measured it right here, or if I measured it right here, right? So it can change based on that, based on which time point you're looking at. So just be aware that the time point that they're specifying is important to determine what the actual point prevalence is. Okay, so the relationship between incidence and prevalence, basically, we're going to look at some AIDS data from kind of the early 80s up through 1992. So I'll kind of show you how to make heads and tails of that. But essentially, this is data reviewed by the CDC. They were starting to use information gathered from 1981 when it was first recognized up through 1992, after which time the comparisons are very difficult to make because your definition of what was considered to be AIDS underwent a pretty big change. And we're going to see that your definition for what you're including as your cases are going to be very important. You don't want that to change over time because then it's hard to really compare apples to apples in that case. So anyway, this is going to show the complex relationship between incidence and prevalence. Okay, so essentially what this is looking at is, one, we're going to see the new incident cases of AIDS that are diagnosed every year during this time frame. So in here, you can see that in 1981, we did not have very many cases because, again, it was a very new disease state. We're just now starting to find people. And as we get better at being able to diagnose it, you see that the incident cases are increasing, right? So the total height of the bar are going to be new incident cases that are occurring, that are diagnosed each year, right? The purple section of the bar are going to be cases that at the point prevalence in 1992, the end of the study period, the number of patients who were dead, right? So essentially you're looking at each year. So everyone that was diagnosed in 1981, by the time 1992 rolled around, all of them had died. And you notice that this is going to be pretty consistent for the first few years, and then maybe as we start to either capture patients earlier or as their treatment starts to get better, you'll notice that now we have a few patients who at 1992 were still alive during here. So the prevalence of alive patients is starting to increase around 1984. And then as we got better with our treatment, we noticed that, again, you had the highest number of people alive at 1992 in that last year. Why do you think that is, besides just the fact that we were maybe getting better at treating patients? We had AZT, so besides just treatment, why do you think this bar is so much wider for 1992 than for any other one? Yeah, so these are new diagnoses, right? So these patients had not been having, presumably many of them did not have the disease as long as someone who had been diagnosed in 81, right? So because they had been diagnosed later, they have not had the same period of time to really for the disease to manifest and them potentially die. So again, your prevalence would be changing had you carried out the time even further. So say you looked at 1999, you may see these bars would change very drastically, right? But because our point prevalence that we're looking at is 1992 for the patients that are still alive, that's why we see that this bar is so much wider for 1992, because those patients were newly diagnosed. So chances are they're probably earlier on in disease progression than people who were in 1981.
So this as far as I guess T1 and T2.
Mm-hmm.
What would be T1 here and what would be T2?
So essentially you're using 1981 as your beginning time period and then 1992 as your endpoint, right? So then what we're looking at with these purple bars is the point prevalence at 1992, right? So we're just looking at one slice at a time. We're saying at the end of 1992, who is still alive in this group? And this is what the white and purple bars are showing us, right?
White also includes the new cases or just the ones that rolled over?
Yeah, so the total height of the bar are all of the new diagnoses or the new incidences that occurred each year, right? Yeah, only the new ones, right? So the people that were diagnosed in 1981 did not get included in 1982, right? Because they wouldn't be an incident case anymore. They just they're continuing to have the disease, right? That makes sense for everyone? Okay, so we'll go into a little bit more detail on that. I don't see too many graphs that are done like this, but this is kind of an interesting one where you can look at the kind of comparing the incidence of new diagnoses versus the prevalence of a certain condition, or in this case, death at the end of the period.
So the purple bar is somebody that died within the year that they were...
No, so the purple bar are the people that were dead at 1992, the end of 1992.
So for 92 though, then those people were diagnosed and died that same year.
Mm-hmm. Yeah, so potentially you caught some of those patients very, very late. Maybe they've been sick for a long time, and then someone finally thought, hey, let's test them for it and see what's going on, and that's what happened, right? But again, that's why the white bars are so much wider, because again, a lot of those patients were probably diagnosed very early and had not had time for the disease to manifest.
15,000 people.
To a lot of people, we did not have a lot of good treatment. And again, because there's a huge social stigma against this, so a lot of people were not coming forth, especially if they were asymptomatic for a long period of time, so they could have been very, very ill when they got the final diagnosis, right? You could have had some, very severe infection or, whatever it happens to be. So. I never said epidemiology was an uplifting subject, but anywho. So again, just to cover that again in detail. So the full height of each year's bar shows the total number of new AIDS cases that were reported to the CDC for that year. The darkened part of each bar is the number of patients in whom AIDS was diagnosed in that year, and they were known to be dead by December 31st, 1992. Right, so that's that point prevalence at the end of 1992. And so the clear space are going to be the number of patients in whom AIDS was diagnosed that year, but presumably still alive. Right, so they had no record that they had died during that period, and then so again you have to look at where your data sources are coming from. If you're only looking at death certificates, perhaps that person didn't have one filled out, or we know where it happens to be. And so the sum of the clear areas represents the prevalent AIDS cases as of that date. Okay, so basically just what we said. So, of the patients in whom AIDS had been diagnosed between 1990 and 92, and who had the disease for a relatively short period of time, a fairly high proportion were still alive at the cutoff date. So we mentioned that, and they probably they were not living with the disease as long as some of the people who were diagnosed very, very early. Again, so due to the recency of infection, also improved treatment. We saw that AZT and zidovudine was becoming more common during that time frame. And if you look at the patients who were diagnosed in the first 6 years of the epidemic, it was almost all fatal, right? Because we really didn't have a good treatment at that time. Total number of cases in an epidemic disease reported over time is going to be the cumulative incidence. So if you added up all of those bars together to get the cumulative number, and I believe the end there was like 253,000, that was basically your cumulative incidence of AIDS being diagnosed during that time frame. So again, looking at the cumulative incidence of AIDS caused through December 31st, 1991 was 206,000. The number known to have died was 133,000. So those bars kind of show that. And at the close of 1991, there were 73,160 prevalent cases. And again, do you think that was the full story? Do you think there were some people that were not diagnosed at that point? Probably, right? Because again, underdiagnosing or underreporting is probably going to be more common here. And so again, in those patients with AIDS died in subsequent years, they would end up being removed from the prevalent case category, right? So again, just depends on where you're setting your point prevalence at to define where your prevalent cases are going to be. So you can just kind of recap the data, what we're seeing there. Any questions on that? Kind of makes sense how you can kind of relate incidence and prevalence to one another. Okay. So then when 1993 rolled around, the CDC made a major change in the criteria for defining AIDS. And so they were seeing that a backlog of patients whose disease manifestations met the new criteria was included in the counts for the first time. So now we could have been misdiagnosing people and not really including in that initial definition that we were looking at prior to 1992. So now all of a sudden you would end up seeing a really increased spike of patients being diagnosed because the criteria had been widened to include more of those patients. So again, more recent AIDS data are typically not as satisfactory as the older data for really illustrating the relationship between incidence and prevalence. So that's kind of why we showed that early set of data. And so I'll show you the next slide here that'll provide an illustration of how important a consistent definition is to defining a disease and to be able to make fair comparisons over time. So here you can see how the incident cases of AIDS was increasing, and then all of a sudden you change that definition in 1993 and you saw a huge spike in it, right? So now you're including way more patients into your grouping based on your changed definition. So again, comparing data from 1996 to data in 1990 is very, very difficult because the definitions are so much different. So that's going to be really important. We're talking about surveillance, and we're looking at how you define your cases in those cases or in those situations.
Do we have like HIV data on who's infected with HIV?
That is probably, because it's a reportable disease, so assuming that data is being reported through the proper channels, then that lives somewhere.
And that would be consistent from all of these time points?
Not necessarily, because again, depends on the definition, right? So again, here we're probably broadly saying AIDS. Who knows what specifically the definition they were looking at. If it was truly an AIDS-defining illness, or they were including all the HIV patients. And it's hard to say what the specific definitions were between time point to time point. Because again, when it's brand new and you don't really know enough about it, there could have been patients manifesting PCP pneumonia and things like that, where you weren't really sure that this was linked back to this condition. So. Over time, fortunately, things are getting more sophisticated, and we can, better delineate those patients. But again, it just makes comparisons over time more difficult. Okay, so again, prevalence is the result of many factors. So again, it can be the periodic or annual number of new cases, the immigration and emigration of patients with the disease. So if they're moving out of the study area or going into the study area, whatever it happens to be. And so the average duration of the disease or the time of onset of the disease until death and healing occurs. So all these different factors can be changing your numerators and denominators from that standpoint. So basically, the following is an approximate general formula for prevalence that is conceptually important for kind of understanding and predicting the burden of disease on a society. So again, if you're kind of looking at what you think the entire population, say, of the U.S. with HIV, one of the things you can do is say, okay, the prevalence, I think, in the U.S. population is going to equal the incidence times the average duration for whatever your period is, right? So again, and you notice that, especially patients with HIV, they're living longer nowadays. So because as they are living longer with the disease, what do you think that's doing to their prevalence in the U.S.? It's increasing, right? Because they're not dying off anymore. They have a lot better antiretroviral treatments and things like that. So they're living longer with the disease, and now they're starting to succumb to other issues like cardiovascular disease and things like that. But essentially, the burden on the society is increasing because these people are living with it for longer. Thus, the increased incidence keeps adding up. So it really only works if the incidence of the disease and its duration in individuals is stable for an extended period of time. And so the implication of the formula is that the prevalence of a disease such as AIDS can increase as a result of increase in the yearly number of new cases. So say something happened to where we were now diagnosing it differently and we were increasing the number of cases that we saw, or something changed where we were having some sort of outbreak of it. And then an increase in length of time that they're symptomatic, patients survive before dying or recovering if that becomes possible, say for whatever type of disease state you're looking at. So looking at the incidence of AIDS in the U.S., we know that it's declining, but the duration of life of individuals with AIDS is increasing, again, especially with more prophylaxis, looking at new antiretroviral agents, being able to genotype the disease to get the regimens specifically right for them. And so you're seeing an increased length of survival proportionally more so than the decline in the incidence, right? So even though we're having fewer new cases because they're living for longer, and that's kind of outstripping the new incidence of cases, we're end up seeing that the prevalence in the society is still increasing. So another example is going to be cardiovascular disease mortality. So looking at age-specific incidence has been declining in the U.S. in recent decades, but the prevalence is not. So again, these patients with cardiovascular disease, we have better drugs for them. They are hopefully living longer because we have better reperfusion techniques and things like that. Hopefully they're living for longer, but that's also causing the prevalence in the U.S. to go up as well. So that makes sense? So as patients live for longer, they're going to be a bigger percentage of the population, or a bigger prevalent slice of the population that's going to have that outcome. Okay. So the next thing we'll look at is going to be risk. We've already talked about risk to some degree when we were comparing different means of say, samples when we were doing studies in biostatistics. So risk is going to be defined as the proportion of persons who are unaffected at the beginning of a study period, but who undergo the risk event during the study period. Right? So essentially the risk event may be death, disease, injury, whatever you set it up as. And what you're basically seeing is that the persons at risk for the event at the beginning of the study period are going to be called a cohort. And so have you guys heard of cohorts before, like cohort-based studies? All right, so essentially what we're going to be doing is basing, kind of dividing groups of patients up into a cohort, maybe based on risk factors, maybe based on whatever happens to be. And we want to see what the risk of that event occurring is, right? So say in a cohort, the denominator for 5-year risk of death of diseases is going to be the same as a 1-year risk because in both situations, the denominator is the number of persons who entered at the beginning of the study. Okay, so it's going to be important that, and here when you're talking about risk specifically, you're going to be looking at the entire group of patients that came into the study as being potentially at risk, and thus they're going to be the denominator, and that does not change no matter what kind of time frame you're looking at, whether it be 1 year or 10 years. If they entered in initially, they're at risk. So it's important to really kind of take care when you're applying actual risk estimates, which are being derived from the populations, to an individual patient, right? Because it's again, that's always going to be the question you're trying to answer. Your patient's like, well, what's my chance? What's my prognosis? What's the likelihood that I'm going to survive this? And so keep in mind that if death and disease and injury occurs in an individual patient for that person, the risk is automatically 100%, right? So you want to be able to take care when you're describing these chances to someone, because if you were to say, what's my chances of survival of this surgery? and you say, well, you're 99% chance going to survive, right? What are they going to think?
Definitely.
You definitely do it when they do it? Or they're like, I'm probably going to be that 1%, right? I'm always that person that's the 1%. I always hear that every time. Especially when like we're giving like drugs to patients and stuff, like, you know, if we're putting them down for sedation, you better get a lot because I'm that one person who always takes a lot. Like, okay, we'll see. So yeah, so they automatically think they're going to be the snowflake, right? They're going to be the 1%. And so really the better thing to do is to try to equivocate it to something that's even more dangerous, right? Or something that's even more risky, or whatever happened, the comparison you want to look at. So again, if you're on a long automobile trip, what are your chances of having a fatal collision? Probably better than 1%, right? Especially the longer you're driving for, especially on the conditions, things like that. So by kind of comparing it and contrasting with other types of risks, you can kind of make it a little bit more solid for the patient to let them know that, okay, you know, this is probably going to be okay for me, right? So just an important kind of counseling point when you're talking to your patients. So often it's going to be difficult to be sure that the correct denominator for a measure of risk. So again, who is truly at risk for an event occurring? Again, if we're talking about the population of women who may be at risk for becoming pregnant, it has to be modified for practical purposes. So as you might imagine, if you were looking at patients who are at risk for becoming pregnant, who do you want to rule out immediately? Okay, so yeah, so women, so put an age range on it, right? So who do you think is going to be potentially possible to get pregnant? So again, rule out men, probably. Probably want to get rid of them, unless you're in like a junior situation or something. It's my second Arnold Schwarzenegger reference today, I'll have you know. So again, put an age range on it. You probably want to get rid of people who are, say, have had a hysterectomy or say are sterile for some other reason. And so that way you can kind of get your denominator a little bit closer to people who actually have risk of the event occurring. So again, just keep that in mind, that it's important to make sure that when you're evaluating the data and evaluating research, that they're adequately defining who that population is. So the truly susceptible population may be especially difficult to know for infectious diseases as well. So ideally, for an infectious disease agent, only the susceptible population or those without antibody protection would be counted in that denominator, right? So that can be pretty difficult to determine in a lot of cases. So as a practical compromise, very frequently the denominator is usually going to consist of either the total population of an area or the people in an age group who probably lack antibodies. And so sometimes you can get that data from things like, look at the immunization status of a group and things like that to try to figure out who specifically is at risk. So looking at the risk of death from an infectious disease can be pretty complex, right? So if you're looking at the subsets of a population, the people who die, or there will be people who will die from an infectious disease, right? And they're going to be a subset of people who are ill from it, who will be even coming from a larger subset of patients who have been infected, who are from a larger subset of patients who have been exposed, and from an even larger subset of those who have been susceptible, right? So not everyone's going to fall into each of those categories. Usually a pretty fair, small number of people are going to kind of get all the way down to the point where they're ill and then potentially die. So because of that, we know that this subset is each subset is a subset of the next and should be a subset of the total population. So it's important to define each of these groups as we move forward to make sure we're looking at the specific denominators we want to look at. So the proportion of clinically ill patients who die, in this case we're going to call this the case fatality ratio, right? So these are going to be patients who are ill that we know have died, so they've already contracted the disease and became symptomatic, so we're going to call it the case fatality ratio. Okay, so that's a good definition to know. The higher the case fatality ratio, the more virulent the infection. So again, you can kind of compare case fatality ratios between, say, different treatment groups, or you can compare them between different types of infectious causes to look at, try to compare which ones are more virulent. And then the proportion of infected persons who are clinically ill is often called the pathogenicity, right? So how many people are being exposed to it who are actually becoming symptomatic from the infection, right? It could be people who get infected who do not become symptomatic. Some people will. So again, that's where you're talking about the pathogenicity of it. And then the proportion of exposed individuals who actually become infected is going to be the infectiousness of the organism. Okay, so again, these are all affecting how your subsets are going to be affected by the different disease states. So again, just kind of showing you how these are just kind of progressively smaller pieces of the same pie, with the kind of the big picture being the total population you're looking at. Board game, risk. I'm just kidding. All right, so we know that the concept of risk is going to have some limitations. So we're going to be looking at this example where we're looking at 3 different patient populations. Let's say we're looking at 3 different nursing homes. And again, we want to keep things depressing, so we're going to talk about death in nursing homes. And so essentially, they're going to have no new patients be admitted to the nursing homes. These are very popular, completely full to capacity. And we're going to assume that they have the same overall risk of death, so 10% for the whole year. And we're going to be looking at the same year, so say from January 1st to December 31st of the same year, X. And we'll see that despite the similarity in risk, because again, they all have 10%. So again, if you had 100 patients, how many should be alive at the end of the year? 90, exactly. So the deaths in the three populations may occur at very different patterns over time, as we'll see. So suppose that population A had a really bad influenza epidemic that was in January, so at the beginning of the study period, and that most of the patients who were going to die during that year died at the very beginning, right? Still 10%, but most of them ended up dying at the very beginning of the year. Suppose that the influenza epidemic did not hit population B, maybe they had a good vaccination, and they did not get hit with it until the following year in December. So they end up having most of the deaths occurring at the very end of the year. Again, still 10%. And then finally, suppose C was never hit with the epidemic, and that the deaths that occurred happened evenly throughout the year. And I'll show you a graph of what that looks like in just a minute. So you see that group A had the most patients died in January, B had most of them die in December, and then C was kind of consistent through all out, but all of them had 10% end up dying during the year. So we would see, we're going to talk about the force of mortality and how that can change based on how patients are kind of having the outcome of interest over time. And so again, the 1 year risk, again 10%, would be the same in all three populations, but the force of mortality would not be. We'll look at how you calculate that in just a minute. So when we do that calculation, we'll see that the force of mortality would be greatest in population A. We're going to see that the least in population B, and then it will be kind of intermediate in group C. And I'll show you again how, so just keep that in mind, and we'll see how that actually calculates out in just a minute. Because the measure of risk cannot distinguish between these three patterns of the timing of deaths, a more precise measure, or the rate of mortality, may be used instead. Because again, we said when we're measuring risk, we're looking at all the people who had the outcome, we're interested in as a numerator, over what denominator. What would be our denominator in the idea of risk in these populations? Right, everyone at time 1, right? So everyone that was initially in the nursing home at January 1st would be your denominator. And so it doesn't matter how they died throughout the year, that denominator doesn't change for them, right? So that's why the risk is going to be the same through all groups, but you're going to see that the rate is going to be changing. So again, looking here, we see that you have roughly 90% survival over here on the right side of the graph with a 10% mortality. And notice how the different populations are changing over time, where most of them died in group A in January versus in B, where most of them died in December. So you see how those kind of differ there. And we're going to see that the rate of mortality changed between the three different groups. So the rate is going to be the frequency or the number of events that occur in a defined time period, so in this case would be a year, divided by the average number of people at risk during the period being studied. So how do you figure out that average number of people at risk? Basically what we can use to determine that is going to be the mid-period population, and that's going to be our best estimate for the average number of people at risk for the outcome during the time period. So again, the mid-period population often is going to be used as the denominator for rates. Right, so not for risk. Risk, you're going to use the beginning denominator of whoever is in your study at the very beginning. With rates, you're going to be using that mid-period point. So the way you divide this out is you just do your rate equals the number of people who had the outcome divided by that mid-period point, and then by some constant multiplier. We'll see what the multiplier is in just a minute. So again, when we're looking at rates, keep in mind that we said that the people who end up dying in an event would be a subset of people who are ill, would be a subset of people who are infected. And you can see how the number gets kind of progressively smaller. So say, for instance, in each of the 5 fractions, if they were going to equal 0.5, or say that every one person who was exposed, you had 2 people who were susceptible, and say that was 0.5 all the way down, you end up seeing that basically 3.125% of the total population would end up dying from this, right? So just keep in mind that there's always going to be subsets or smaller populations within a total population. We'll see how that kind of influences rate in just a second. So risk and rates usually are going to have values less than 1 unless the event of interest can occur repeatedly. So again, because death can only occur, say, once, in that situation, it would always be less than 1. Unless you had every single patient end up dying, then it would just be 1. So 1 or less. If the event can occur frequently, so say you're looking at asthma exacerbations, say you're looking at falls, whatever happens to be, that one can certainly be over 1 in that case. So when you're looking at these numbers, it's oftentimes pretty awkward to talk about fractions of a death. You don't want to say, well, 1/1000th of a death per year. So that's where we get that multiplier from, to try to make it into terms that people can better understand. So say, for instance, you'll see that rates are usually being multiplied by some sort of constant, either 100, which can make it a percentage, 1,000, 10,000, or 100,000 to make the numerator larger than 1 and make it easier to discuss. So say you had 1 death per 1,000 people per year. So if you had 1,000 people looking over 1 year, you'd say you had 1 death during that time frame. That's easier for people to kind of understand, to kind of equivocate between different rates than you would say you had 0.001 people die, because that doesn't really make sense. So when a constant multiplier is being used, the numerator and the denominator are both being multiplied by the same number, so the value of the ratio doesn't change at all. Okay, that's why you frequently see the number of deaths that occurred. It doesn't change the ratio, but that's how it's frequently going to be reported in the literature. So we'll look at crude death rate, and this is going to be why the constant multiplier is going to be useful here. And so in 2003, the rate for the U.S. was about 0.0086 per year, but by multiplying it by 1,000, we were able to express it as 8.6 deaths per 1,000 individuals in the population per year. It's a little bit easier to talk about, people kind of making a better heads and tails of 8.6 deaths, even though it's still kind of a fraction, rather than saying 0.0086. Most people can't really, kind of mentally make that jump to say, what does that really mean in a true population? But if I said I have 1,000 individuals and I know that 8.6 of them will die within a given year, that gives me a better idea of the actual number, the actual implications of that. Rates can be thought of in the same way as velocity, and so it's possible to talk about the average rates or average velocity for a time period. So, the average velocity is obtained by dividing the miles traveled. Say, 55 divided by the time frame you went over. So in an hour. So again, if you were driving 55 miles for an hour, you'd be 55 miles per hour. Now, it does not mean that the car was traveling at exactly 55 miles per hour for every instant during the hour, but it says it averages out basically to that. And the same thing we're going to be looking at here. We're looking at averages, not specifically how many people are dying, say, every single day. So in a similar manner, the average rate of an event, say death in this instance, is equal to the total number of events for a defined time period, say over a year, divided by the average population exposed to that event. So if you had 12 persons per 1,000 persons per year, right? So if I had 1,000 people, I know that 12 of them would end up dying over that year time frame. And so the rate can be thought of as kind of describing the reality at an instant in time. And so this is sometimes called the instantaneous death rate or a hazard rate. So kind of another way to look at that. And so because death is a discrete event rather than just a continuous function, instantaneous rates cannot be measured at an instant of time. They can only really be estimated. So again, all of these are going to be averages. They're kind of estimates of kind of this force of mortality that we're looking at here. So looking at the relationship between risk and rate, in the nursing home example, the populations A, B, and C were all similar in size. Each of them had a 10% overall risk of death in the same year, but their patterns of death we saw differed pretty greatly from one to another. And so the next slide will demonstrate the 3 different patterns and illustrate how, in this example, the concept of rate is going to be superior to the concept of risk when showing the differences in that force of mortality. So again, you can obviously hear that the force was much greater in group A because they had the most deaths occur at the initial period. And so what do you notice about the differences here between the mid-period populations? Who has the highest? Right, group B has the highest, right? And so why did they have the highest one? Because when did most of the people end up dying?
They died at the end.
Yeah, they died at the end, right? Versus in group A, they had the lowest mid-period population because they end up all dying kind of at the very beginning of it, right? So you can see how this is changing this mid-period population based on basically the rate of people dying in that group. Even though the risk was the same all the way throughout, you can see that the velocity was higher in group A because at that point, what is this doing to your denominator? If I was, say, going from C to A, what does that do to my denominator? Get smaller or bigger? Get smaller, right? So that makes my total number, my ratio, even larger, right? So that's why you can see that force of mortality is increasing by using the different mid-period populations. So again, because most of the deaths in population A occurred before July 1st, the mid-period population of cohort A would be the smallest of the three populations, and then that resulting death rate would end up being the highest, right? So the rate would be highest, the risk is all the same here. Because the denominator is the smallest and the numerator is going to be the same size for all three populations. So, if you had 100 patients in each nursing home, again, they're all going to have 10 patients that died during that time frame, but your denominator is what's changing here. Because most of the deaths in B occurred at the end of the year, they're going to have the lowest rate because, again, they are going to have the largest denominator because most of their deaths were kind of back, were done all at the end of the time frame. And then C would end up being intermediate because they kind of all died at a consistent rate throughout the time frame. So even though the one-year risk did not show differences in the force of mortality, the rates were able to do so by reflecting more accurately the timing of the deaths in the three populations. So rate is often going to be used to estimate risk. You'll see that rate is generally going to be pretty similar to risk, especially if the event in the numerator occurs only once per individual during the time frame. So these are important points to remember when looking at risk versus rate. Usually want to be seeing that the proportion of population affected is going to be pretty small. So again, it could be death, it could be a good one depending on the type of patients you're looking at. And if you're looking at a relatively short time frame. So rates are going to be better when you're looking at shorter time frames because you're not going to see as big of a change in that mid-period population. So obviously, if I kept looking at these nursing homes over a period of 5 years, what do you think that would do to my mid-period population? Saying I had no new patients coming in or out.
Decreasing.
It would keep decreasing because I keep having 10% of that population die every single year. So keep that in mind. So again, if the time interval is long or the percentage of people who die is large, the rate is going to end up being noticeably larger than the risk. Because again, as that mid-period population keeps decreasing, as I increase the amount of time I have, the denominator is getting smaller, thus the rate is getting larger. So if the event in the numerator occurs more than once during the study, as can occur with colds, ear infections, things like that, really what you want to be looking at is going to be incidence density. This is going to be a better measure for this. So rates are going to be better for things that occur just once. Incidence density can be used instead of a rate for things that occur multiple times. So although the denominator for the 5-year risk is the same as for the 1-year risk, when looking at risk, because again, we're using the initial patient population, that would not be true for a rate. So again, if you think about it, if I had that same 100 people in a group, and I was looking at risk over time, that denominator never changes, because again, risk, no matter how long I'm looking at it, it's always going to be the initial group of people that are at risk that I'm looking at, versus rates, you'll notice that changes because we use that mid-period population. When using things that can happen multiple times, I'm still looking at that same initial group of people because that can happen multiple times. If I'm using rates, when someone's died off, they can't really be included in that number anymore. So that's where the big difference is here, where things that can occur multiple times are better to use with incidence density. So looking at rates, the denominator we know is going to be constantly changing. So if it can decrease as some people die and others can immigrate from the population. The denominator could increase if you had some people kind of move into the population, immigrate in, or others that maybe are born into the population. So again, you can see that your denominator kind of changes over time. And so rate is going to reflect these changes by using that mid-period population as an estimate of the average population at risk. It may not be perfect, but it's going to be your best way to be able to compare different rates of things together. So as noted earlier, a rate may be a good approximation of risk if the time interval in the study period is going to be short, because again, our denominator should be relatively close to one another versus if we're looking at a longer time frame. If the interval is going to be long, the rate is going to be higher than the risk because the rate's denominator is progressively reduced by the number of people at risk going down. So when the risk and the rate and the risk are small, the differences between rate and the corresponding risk are also going to be pretty small as well. So again, the smaller the number of people being affected by this, the shorter time frame, the closer risk and rate are going to be together. Okay. So these principles can be shown by examining the relationship between mortality rate and mortality risk when looking at population C. So specifically, C had a very consistent decrease in patients over time, right? They were the ones that didn't get hit by any influenza epidemic. So they had an even mortality risk throughout the entire year, and presumably they would continue to have a even mortality risk continuing ad infinitum, right? So by the middle of the year, if we knew they had 10% risk, by the middle of the year, what percentage of patients of those had already died? Yeah, it should be half of that 10%, right? So 5 of them had already succumbed, right? 5% roughly. So looking at that, the mortality rate would end up being 0.1, because that's our risk, divided by that mid-period population, or 5 minus 1, or I guess 5 minus 100. So you end up getting that 0.1 over 0.95. Equal that out, and basically your rate there is going to be 105.3 per 1,000 persons a year. Make sense how that number came about? All right, so what would be my constant here that I multiplied this by? Yeah, it's 1,000, right? So, because again, it's hard to say that, okay, well, 0.1 of those people are going to die, in this population. That doesn't really make sense. But if I said 105.3 per 1,000 persons per year, that makes much better sense to people, right? So notice how that is larger than if you were just to look at the risk of death, right? If I had done that same calculation, but just looking at risk, where my denominator is just going to be that initial 1, what would that risk be? So if I were to still multiply by 1,000, so it said 10% times 1,000 would be 100, right? So notice how the risk and the rate are pretty similar, but you notice here that the rate's going to be a little bit higher. And right, that's all going to be in relation to the denominator changing, right? Because I had 5% of those people die by the time that the mid-year rolled around. That makes sense? They're close, but they're not going to be exactly the same because the denominator changes. So, and so the yearly rate is going to be higher than the yearly risk because the average population at risk is smaller than the initial population at risk. Just go back and remember how we're calculating those a little bit differently. So again, right here you have about 5% of the people that have died. That's your denominator. Okay, so so what would be the cumulative mortality risk for population C at the end of 2 years, assuming you kept that constant yearly mortality rate of 0.1053? Okay, because notice at the beginning of year 2, how many patients are at risk had you had no change in the population? Because at first year we had 10% of 100 die, so at year 2 we have how many left? 90, right? So how many people are at risk for death during year 2? Yeah, still 10%, but now it's 10% of 90 and not 10% of 100. Right? So notice how this is changing over time. So this is why the math is going to get more complicated as you look at death rates and mortality rates over a longer period of time. So I'll show you how the math works out for that. So it could not be calculated by simply multiplying 2 years at the yearly risk of 10% because that number of still living is subject to the force of mortality by the beginning of the second year, and thus it would be smaller. So we'd have, say, 90 patients to start with rather than 100. So the cumulative risk of death over 10 years could not be calculated just by multiplying by 10, because again, if you just did 10% times 10, you end up getting how many patients are dead? You say all of them would be dead, right? 100%. If it was 10% every single year, so 10% of that initial 100, so 10 people died the first year, 10 people died the second year, 10 people, by 10 years, how many people are dead? 100, right? So then I got no people left in my nursing home, not making any money. Not good. So, but we know that's not the case, right? It's always going to be 10% of whoever's left in that population each single year, right? So we know that it's not going to be, we know there's still people left at the end of 10 years based on that. So there's going to be a straightforward way. You guys might not think it's straightforward, but I'll show you how. We're going to determine the cumulative risk based on the number of years. So essentially what we're going to do is calculating that cumulative mortality risk in the patient population with constant yearly mortality rate. So first part, you have to start with your beginning data. So we know that population C has an even mortality risk throughout the year, and they have a total yearly mortality risk of 10%, right? By the middle of the year, we know that death has occurred in 5% of them, so we have 95 patients left, for instance. And then when we multiplied that out, we got the mortality rate basically being 0.1053, or if you multiply that by the constant of 1,000, basically 105.3 people per 1,000 people per year. So again, at this rate, remain constant, what would be the cumulative mortality risk at the end of 2 years, 5 years, 10 years, and 15 years? We can figure that out using some natural logarithms. Yeah. This is actually, when we look at this is going to be very similar to how we actually do pharmacokinetic calculations, actually measuring blood levels and determining what a person's, we can extrapolate what a person's blood level would be later on in a given time frame. So actually this is kind of interesting how these are kind of paralleling one another. So basically the formula is going to be that the, basically is R for whatever time frame you're looking at. So R is going to be your risk. T is the number of years of interest. And then E is going to be that base of natural logarithms, right? So you guys have seen that symbol on your calculator at some point, right? Yep, we're going to use it. And then this mu is going to be the mortality rate that we're looking at. So that was going to be our constant that we're going to be multiplying that by. And so basically you're going to be seeing that your risk for any given number of years is going to equal 1 minus the natural logarithm raised to the power of your rate times your time frame. You take the negative of that and you'll get your answer. So we'll show you how that works in just a minute. So how do we calculate that in this case? What we're going to do is say that for 2 years, what we can do is plug all those numbers in. So you can see where our constant fits in here, that 0.1053 times 2 years. Go ahead and multiply all that out and you end up getting this number here. And then when you calculate that out, you end up having basically what's left is 0.1899. So what does that mean for you? Basically it means that you basically, after 2 years, you have a 19% risk of death. So again, if you were just to say, just go with the yearly risk of 10% each year, you might say 20 if you just multiply it by 2, but that's not the case, right? Because we know fewer people at risk at year 2 than there were at year 1. So in this case, after 2 years, you could say you have a 19% risk of death in over 2 years. We can see how that will be even further extrapolated. I could look even further into the future, say 10 years, 15 years, whatever you want to look at, just by changing out the numbers. Because again, we say that our force of mortality, or that constant, is always going to be the same as we go forward. So the ways you could calculate this, if you wanted to do this on a handheld calculator, I'm not going to make you do this on a test, but just so you know, for your purposes, essentially to calculate the cumulative risk on a handheld calculator should have a key for natural logarithms. So a key for logarithms to the base E, or that 2.7183 for any math nerds out there. And so the logarithm key is usually labeled as ln, not the log key. So it would be a different base there. So you want to use the ln key. And so essentially you're going to be entering in the number of years. So in this instance it was 2. You would multiply that by your constant, or mu, which in this instance would be 0.1053. So you multiply those two together. You're going to hit the plus minus key because you want that to be a negative. Right? And then you're going to end up hitting the inverse button, and that'll switch over the sign to negative, and then you'll hit the ln button. So basically that's going to give you that e raised to that power of your constant times your time made negative. So you get that, and then essentially you can put that into memory, and then do 1 minus that number, and then you get your cumulative risk. So again, you shouldn't have to do all that too frequently, but just so you know how you could do it on a calculator. Again, we do this very frequently pharmacokinetic calculations. Essentially what we can do is take 2 blood levels of a drug, and I can figure out what that rate constant of degradation of drug is over time, and then apply that to future time frames to see what their blood level would be, say 6 hours from now, or 12 hours from now. So just so you know, there is real world application for these kind of calculations. So based on that, if you were to plug in different numbers, say 2 years, 5 years, 10, 15, you can see how your cumulative risk of death is going to be changing over time. So again, it keeps going up because again, you're still going to have, as you go further along in time, you're going to increase your risk for death. But notice it's not going to be just straight multiplying by the number of years. So by the end of 10 years, it's 65% risk of mortality. By 15 years, it's 79%. Because again, even at the end of 10 years, you still have some patients left over who are still at risk. Does that make sense? So this is why we do cumulative risk this way versus just kind of multiplying the overall risk times the number of years you're looking at. Okay. So to be valid, a rate should be meeting certain criteria with respect to the correspondence between the numerator and the denominator. So first, all the events counted in the numerator must have happened to persons in the denominator, right? You don't want to be kind of mixing up your groups. If people either left the study or came into the study, whatever happens to be, you want to make sure whoever was having the event is actually calculated in that denominator. It should be captured there. And then all the persons counted in the denominator must have been at risk for events in the numerator. So for instance, if you're looking at rates of cervical cancer, your denominator should not include men, right? It's a very odd man. I don't know. Whatever happens to be, you don't want to include men in it. So only people who are at risk. Again, if you were looking at patients who are at risk for pregnancy, you don't want to include a 2-year-old, unless you have a very odd 2-year-old. Again, so again, only include those patients who are at risk. So before comparison of rates could be made, though, the following should also be true. The numerators for all groups being compared must be defined or diagnosed in the same way. So again, if you don't want different definitions, because then you're kind of comparing apples to oranges, right? So you wouldn't want to use the definition for AIDS from 1990 versus 1996, because again, that wouldn't work. The constant multipliers being used should be the same. So if you're using, say per 1,000 people per year, that should be the same consistently amongst groups. And then the time interval should be the same. Why do you think that is? Yeah, because it's a rate, and your denominator is constantly changing based on what your mid-period population is going to be, right? Risk could be compared together because your denominator never really changes in that situation. But for rates, they certainly do, so the time frame should be similar. Okay. The numerators may not be as easy to compare if the quality of medical diagnosis can differ over time. So say, for instance, in the late 1800s, there was no way to diagnostically categorize myocardial infarction, but certainly a lot of people died of acute indigestion, right? So by 1930, the situation was reversed, and really almost nobody died of acute indigestion, unless you maybe went to Texas de Brazil and had a really bad night, but many died of myocardial infarction. So can you compare people who are diagnosed with acute indigestion who died in the 1800s versus people who die of myocardial infarction nowadays? No, right? Because the diagnoses are completely different. The definitions are completely different. It's hard to say whether this was, sure, it could have been an MI. It could have been something else. So, could have had a perforated esophagus, or who knows what it could have been. So lots of different things could be affecting this. So again, make sure your definitions are going to be the same. So another example of problems in studying causes of disease over time relates to the changes in the classification commonly used. So you guys are familiar with the ICD coding system, right? So we recently made a switch between
9 to 10.
Yeah, we went from 9 to 10. So again, on the pharmacy side, we never really deal with ICD 9 codes or 10 codes, but you guys certainly will in your charting and whatnot. So looking at this, you can see that these numbers will change over time, so it's important to make sure you're kind of doing apples to apples. So in 1948, there was a major revision to the ICD coding, and so following sudden major changes in the reported numbers and rates of many diseases. Right, so now we have a better classification scheme. We can start to classify these patients better, and now we're all of a sudden having these new rates of things that are popping up, which may not be actually new. It's just things we may not have been capturing before. So not only is it difficult to track the changes in causes of death over time, it's also difficult to make those fair comparisons and cause-specific rates of disease between populations, and especially between countries. So especially if the documentation is not very good in one country versus another, that can be very difficult to compare. Different nations would have different degrees of access to medical care, different levels of quality of medical care, and especially available to most who are dying, or different styles of diagnosis. All of these things can be affecting your numbers and skewing them one way or another. So that's why it's difficult to control for those confounders. So again, just an example, we just moved to the ICD-10. So again, maybe we'll have even newer rates of things that are popping up because we can better classify them. So looking at a few different types of rate that we can view. So incidence rate, this is going to be calculated as the number of incident cases over a defined study period. So kind of what we were looking at those in the case of the nursing homes, divided by the population at risk at that midpoint study population. So again, incidence rate is usually expressed as either per 1,000, 10,000, or 100,000 population per your time frame. Prevalence rate, this one is actually a proportion and not really a rate, but what we'll see here is that it's going to be used to indicate the proportion, usually going to be a percentage of patients who had a defined disease or condition at the time that they're being studied. So basically, prevalence rates can be applied to risk factors and to diseases or other conditions. So basically what we're saying is that, again, when we're looking at the prevalence, we're looking at a single time frame, versus with incidence, we're going to be looking at things kind of moving forward, and we're catching new people who are developing the condition, versus just looking at a population at a snippet of time to say who had the condition, and then we can look back and see what the the risk factors were.
How does prevalence relate to morbidity in the disease?
It can relate back to, so say you're looking at the prevalence of, say, heart disease in the population. You're then going to start to stratify based on, say, like risk factors and things like that to determine what were the causes that led to that outcome. Versus when you're looking, say, prospectively, if you're looking at incidence, if you had two cohorts, you'd say, like, okay, well, I'm basing these people based on their risk factors and then seeing what their risk of developing the condition was. So it's kind of how they kind of relate to one another. So, and then we mentioned incidence density previously. This is going to refer to the frequency of new events per person time. So say per person over so many months or person years. And so for instance, if we had 3 patients who were followed after tonsillectomy, TNA, for recurrent ear infections. And again, we're using incidence density for things that can happen more than once. And so if we were to follow one patient for 13 months, one for 20 months, and one for 17 months, and if they, between them, had 5 ear infections that occurred over these 3 patients, basically what you could say is that the incidence density would be 5 infections per 50 person months, or a follow-up, or 10 infections per 100 person months. So see the difference there is that this can include things that are occurring frequently or more than once versus with our mortality rates and things like that. That was only for one single time event. Okay. So incidence density is going to be especially useful, for things like MIs that can occur more than once in a person, colds, acute otitis, and they can occur more than once during that study time period. And again, very frequently, if you're looking at, say, a small number of patients, you just add up the number of months that they were at risk, divide that by the number of events that had occurred, and that way you can start to make those comparisons. And notice that, if you had one study period where you're looking at these patients over 50 months and you had another group that you were looking at over 100 months, you could just double this rate to be able to compare them a little bit closer together. Okay. So the rates of risk are usually used to make one of 3 types of comparisons. So the first one is going to be the comparison of an observed rate or risk with a target rate or risk. So in this case, we're looking at, say, setting national health goals for 2010 and included expected rates of various types of death, such as infant mortality ratio. And so when the final statistics are published, the observed infant mortality ratio for the nation and for subgroups will be compared with the target objectives set by the government. So again, they're going to say that this is what we should be at by 2010, and then we'll look at our rates in order to see, is that consistent with, or are they less, are they more, whatever happens to be with the goals that were set for us. Second type could be if you are looking at 2 different populations at the same time. This is probably the most common type you're going to be looking at. So instead of having a goal set for you, you can compare rates of death or disease in 2 different countries, states, ethnic groups, whatever you want it to be, say for the same time period. And so for example, if we're going to be looking at a treatment in a control group in a randomized controlled trial for, say, a new medication, you're looking about it for a specific outcome. Those 2 can be compared for sure. A major research concern is to ensure that the 2 populations are very similar and they're going to be measured in exactly the same way. So again, make sure you're looking for confounders, make sure the groups are similar to one another. You don't have age being skewed one direction in one group versus another, things like that. The third type is going to consist of comparisons of the same population at different time periods. So in this case, you're going to be studying for time trends in that population. So we know there's going to be trends over time in the composition of a population. So say in the U.S. we have an increasing proportion of elderly patients because again they're living for longer. Baby boomers are starting to hit the elderly age, and so you can see adjustments being made for such changes before concluding there are real differences over time in disease rates. Right, so we can adjust for the differences in age in a population between say 1960 versus now, make adjustments for those ages and see did the incidence of disease or prevalence of disease really change over time. And then here another concern is going to be that change is usually diagnostic capabilities. So as we mentioned, being able to diagnose MI in the 1800s versus now, obviously it's going to be much different. And so again, you're not really comparing apples to apples in that case. So there are 3 broad categories of rates. We'll talk about crude, specific, and then standardized. How we're going to be comparing those. So as you might imagine, what do you think is a crude rate? It's actually a rate that did not wear pants. Just kidding. No, so yeah, it's kind of not adjusted, right? It's just a. I have to keep you guys awake somehow, right? Okay. So it's just a crude rate. It's just something, just a basic number. This is what actually occurred, right? So we're not really adjusting it whatsoever. So when a population is divided into more homogeneous subgroups based on a particular characteristic, so say we're looking at age, sex, race, whatever it happens to be, and the rates are calculated within these groups, you can call those specific rates, right? So you can look at crude rates for an entire sample you're looking at or population, and then you can then break it down into specific rates. So if we're looking at age specific, sex specific, whatever it happens to be, those are kind of a variation of those crude rates. We'll talk about standardized rates a little bit later on in the course. don't know why I did that. So crude rates are going to be valid rates, but they're often misleading, which is why they're often named crude, right? So a good example of this is going to be guessing which one do you think these three countries between Sweden, Ecuador, and the U.S. has the highest and lowest crude death rate? Who would guess? I think Sweden has the lowest. Okay. Why do you think that? All the fish they eat?
They're good genes.
They're good genes? Wow. It's making a big assumption there. Just kidding. Okay, so again, we can compare crude death rates. And so if you looked in 2004, Ecuador had the lowest crude death rate and Sweden had the highest. I know, right? This is why crude death rates can be difficult to look at. So even though Ecuador had the highest age-specific mortality rates and the shortest life expectancy, Sweden had just the opposite. They had the longest life expectancy, and they had the lowest age-specific mortality rates. So this is why it's important to look at standardizing the numbers so that you can make these comparisons a little bit better, right? So again, if you think about it, Ecuador probably had a younger population that was skewing those numbers for actual mortality, because we know younger patients tend to not die as frequently as the older patients do. So we'll look at how we can adjust for that to make the comparison a little bit more fair. So, this apparent anomaly occurs primarily due to crude death rates not taking age into account. So again, the age of the population, how that's skewing can really affect your numbers. So for a population with a young age distribution, such as Ecuador, where the median age is 23, why do you think we use median age? Yeah, outliers, right? You could have that one grandma is like 120, and then you could have lots of little babies and stuff skewing the number. So by looking at median, you kind of remove the outlier effect there. And also, the birth rate is going to be relatively high, right? You have a younger population, they're going to be reproducing more frequently, and thus the crude death rate is likely to be pretty low. In contrast, for the older populations such as Sweden, they have a low crude birth rate and a higher crude death rate would be expected just because they're skewing older, right? They're not reproducing as frequently, and they're also, older patients are just more likely to succumb to mortality. So age is going to have such a profound influence on the force of mortality that an old population, even if it's relatively healthy, like someone like Sweden, would inevitably have an overall high death rate. And so investigators really should never make comparisons of the risk of death or disease between populations without controlling for age. You should control for other factors as well, like access to healthcare and things like that, but age is going to be one of the big ones, a big confounder you want to take out of the equation. So looking at the comparison between the three groups, and again, this is in 2004, it's a little bit dated information, but you can see the crude death rate, how it's being compared here between the two. And there's how the life expectancy is lowest in Ecuador, but the highest in Sweden, and thus they're going to be, just in general, dying more frequently. So why not avoid crude rates altogether and use specific rates? Well, there could be lots of circumstances where it's not possible to use specific rates. So imagine if the frequency of death or disease, in this case would be the numerator, is unknown for the subgroups of the population. So say you just get a crude number that says, hey, this many people died out of the whole population. And you're like, well, how many people aged 70 to 80 died? Like, we don't know, right? So it's hard to do age-specific rates at that point. If the size of the subgroups is unknown, so again, I don't know how many patients are aged, say 70 to 80, that makes it difficult to make that calculation. And then if the numbers of person at risk are too small to provide stable estimates of the specific rates. So if you have a very few number of people who are at risk for an event, and that number does not stay stable from time period to time period, that can make it also difficult to compare. So if the number of persons at risk is large in each of the subgroups of interest, then specific rates do provide probably the most information. So if you have large raw numbers to work with in those specific groups, then that's probably going to be one of your better bets to look at. So what we can do, although the biasing effect of age can be controlled in several ways, the simplest way we're going to do this is to calculate the age-specific death rates so that the rates can be compared with similar age groups. So you can use the following formula. You can basically do the number of deaths to people in a particular age group, defined by your place in your time period, over the mid-period population, right? So this is a rate we're looking at, times 1,000, or whatever your constant you want to be. In this case, we're going to be looking at 1,000 being the most common one. So crude death rates are the sum of the ASDRs in each of the age groups weighted by the relative size of each group. right? So we're taking into account what proportion of the population falls into each of those age groups in order to make sure that we're weighting those appropriately. So in this case, we're going to see that the underlying formula for any summary rate is going to be as follows. So basically, it's going to be the sum of the individual weights, or the proportions of each age-specific group, and then the rates of the corresponding age group. So the rates and the weight of that population all added up together to create the entire population. So we'll look at the slide in just a second that will kind of demonstrate that. The formula is useful for understanding why crude rates can be misleading, because obviously if you're skewing one way versus the other, it's hard to make comparisons between those two populations. And so the relative weights, or the sizes of the old and the young populations, are different, and then the high and the low ASDRs have different weights. No fair comparison really can be made between here. So this is why we can help to standardize these to make them a little bit easier to look at. Similar problems will also pop up when investigators want to compare death rates in, say, different hospitals to measure the quality of care. So for instance, when I kind of mentioned this before, but when you're looking at, say, a NICU, neonatal intensive care unit, and you're looking at a place that has a birthing hospital versus one that doesn't, which one do you think would skew worse in their mortality rates?
The one that doesn't,
Why the one that doesn't?
because you're not accounting for births. There's no births to offset it, right?
Right, so essentially what kind of patients are we getting transferred to our NICU? The sick ones, right? Because again, when you're in a big NICU, you're more likely, in a birthing hospital, you're more likely to see those healthy patients pop up too, right? So their mortality rate, infant mortality rate, will probably be looking pretty good because you have a higher proportion of healthy patients. When we get NICU kids transferred over, say, to Nemours, they're more likely to be sick because they can't be managed at whatever hospital they're at, or they don't have a NICU to manage those patients. So even though your mortality rates may look higher, you also have to account for the acuity of the patients you're looking at. So it's another confounder that can really skew the results. And you need to look at, again, the weight of those patients and what they're providing towards the numbers, and also whatever disease severity, whatever your confounder that you're trying to account for. So otherwise, the hospitals that care for the sickest people will be at an unfair disadvantage. If you imagine if you're looking at, say, a level 1 trauma center versus a kind of podunk, middle of nowhere hospital with a regular ER, which one do you think would have worse mortality rates? Probably the trauma center, right? A lot of those guys are very, very sick or very, very injured and are not going to do too well. So again, you have to take these comparisons into account. So lots of different reasons why you may need to look at that. So again, these standardized rates, you can also call them adjusted rates, are going to be the crude rates that have been modified or adjusted to control for the effects of age or the other characteristics that allow for those valid comparisons to be made. So you obtain a summary death rate that is free from age bias. The investigators have to age standardize it or age adjust the crude rates by direct or an indirect method. I'll show you what those methods are in a minute. You'll see that standardization should usually be applied to the death rates, but may be used to adjust any type of rate. So it could be based on disease severity, could be due based on race, gender, whatever you want it to be. So we can do direct standardization. So this is going to be the most commonly used method to remove the biasing effect of the differing age structure on the different populations. And so in the direct method of standardization, you take those age-specific death rates of the 2 or more populations to be compared, and they're applied to a single standard population. So basically you're saying, okay, if I take these same kind of death rates and I apply them to a standard population, how do they kind of show up to one another? This is done by multiplying each ASDR, or the age-specific death rate from each population, to be compared to the number of persons in the corresponding age group in the standard population. I'll show you a slide on what that looks like in just a minute. Because the age structure of the standard population is the same for all of the death rates that are being applied to it, the distorting effect of having different age distributions from the real population is going to be eliminated. And so the standard population may be any real or any realistic population, and is often going to be a larger population of which the populations can be kind of compared. So imagine if you're looking at, say, death rates between 2 different U.S. cities, you might take one larger city that's in a similar area to compare to in order to get rid of that kind of biasing effect, in order to make sure that you're really comparing apples to apples. So the direct method is going to show the total number of deaths that would have occurred had you applied those rates to the standard population, and what would have happened there. So the total expected number of deaths from each of the comparison populations is divided by that standard population to give you this standardized crude death rate. So again, it's still a crude number, but it's being standardized to that population. And then both populations are going to be basically being adjusted for that. And so they can be compared other death rate standardized using the same standard population. Direct method may be applied to compare incidence rates of disease or injury and death. So again, not just death, but other things can be compared as well. And then these standardized rates are obviously fictitious because we're basically simulating the data to some degree. And so you don't want to take that to be the absolute truth here. But basically, they're kind of a what-if analysis. You're basically comparing them to say, okay, well, if this had happened in a larger population that's standardized, how would these two groups end up comparing to one another? So a good example of this is going to show up in the next slide, but basically we have two populations, A and B. They're being divided into both young, middle-aged, and older people. So whatever the definition for that we want to be, I will say that. And the ASDR for each age group in the population B is twice as high as that of the corresponding age group in population A. So the death rates in B are higher than we would see in A. So in this example, the standard population is simply the sum of the two populations actually being compared. So basically, I added the populations together, and you'll see that population A has a higher overall accrued death rate than population B. I'll show you what that looks like in a second. And then despite the fact that the ASDRs in B are twice as high as the ASDRs in group A. So after the death rates are standardized, the adjusted death rate for population B correctly reflects the fact that its ASDRs are twice as high as ASDRs of population A. So this looks fun, right? Okay, so basically what we're going to be looking at is, see part one, we're seeing the calculation of the accrued death rates that are occurring in each population. So we're looking at population A here. Let me get my laser pointer. Right, so we're seeing here we have age groups, so young, middle-aged, and older. We're saying the total population here is 10,000. You can see how the age are broken up between the young, middle-aged, and older people. And then you have your age-specific death rate that occurred in that population. And then based on that, you see what your number of expected deaths occurring were, right? So if you had 1,000 of the young patients, their death rate was 0.001. You expect one death per that year. Versus we're looking at population B. What do you notice between the population sizes here? Yeah, so what do you notice about population B? Yeah, they're skewing more young towards the younger patients, right? So even though their age-specific death rates were higher, you'd expect a higher number of deaths here. You notice that a higher proportion of people are dying in population A than B, right? So even though the rates were higher in B, they simply had fewer older patients for them to really reflect that. And so if I were to say, look at 20,000 patients, and so I combine both of these young populations together, so I'd have 5,000 young patients, 10,000 middle-aged patients, and 5,000 older patients. And you can see here, this is our fictitious population we're applying these numbers to. You can then start to compare the death rates to one another. And so we'd see here that if you had this standardized population, group A would end up causing there to be 605 deaths that occurred, versus having 1,210. So you can see here that when you do this standardization, you can really see that Group B really does have twice as high the death rate as Group A does. Does that make sense? So again, this is just a what-if analysis, just saying if I were to apply this to this fictitious population and I take out the effect of age, because again, the age is now standardized across both populations, to actually make a true comparison to see which one had the higher death rate. Okay. I'm going to leave you there for today, and I will record the rest of this and attach it to lecture 13, and you guys will watch that before Monday, right? Yes, absolutely. Watch it before Monday. All right, see you guys then. Have a happy Thanksgiving.